Okay. Welcome everyone. It's my great pleasure to welcome Sriram Ramaswamy to our Theory of Living Systems webinar series. For those of you that don't know, Sriram Ramaswamy, FRS, I should say. So Sriram's a fellow of the Royal Society. He's a professor at IISc in Bangalore. Sriram, he was also director of the Tata Institute or Center for Interdisciplinary Sciences at Hyderabad for a while. But I suppose the most important thing is Sriram's one of the sort of founding fathers of active hydrodynamics, and still very much a leading light. And it's a pleasure to have him here. So before we get started, I'll just mention a few very small things, which is that obviously for questions, you can either put them in the Q&A or in the chat, whichever's easiest for you. And I'll just try and keep an eye on them. If you're happy to go live, you can just sort of put that, and I'll when the time comes, I can just unmute you or allow you to unmute yourself, in fact, and then you can ask a question. Otherwise, I'm happy to just ask the questions by reading them from the comments. So that's seems to have worked okay in the past. And yes, and at the end of the talk, what we've been doing is rather than closing the call, is sort of kind of ejecting everyone, which is a bit weird, but it just is the only way we've managed to make it work with this Zoom webinar setup. So sorry if you are sort of unceremoniously dumped off. I will give you fair warning. So without further ado, I'll let Sriram take it away.
Thank you very much, Richard, Sami, Michael, and all the organizers of Theory of Living Systems seminars. I'm really very pleased to be giving this talk. I dreamed up a slightly funny title for it in the hope that it will entertain people. But it's about active matter. That's where I am, and that's where my support comes from. So I'll tell you a bit about active matter in a general sense and non-mutual or non-reciprocal interactions. And then I'll take you actually in a sort of an excursion through 4 different settings in which these ideas play out. So each will be a bit short. A question to Richard before I get further. Did you say that people can interrupt during the talk, or do you not want them to? I'm happy to have them interrupt.
Actually, so in principle, they can't, even if they wanted to. But they can. Okay. Yeah, so they can type into the chat, and if anyone has a burning question, they can type that into the chat, and I can maybe interrupt for them if you're happy with that, Sriram.
That's fine.
But mostly people have been just waiting until the end.
Okay, that's fine. But one question, because the talk is in 4 parts, we could also do pauses between these parts for questions, if you like.
Okay, well, why don't we try that and see how it goes.
So I'll tell you about these topics, which seem fairly diverse. Let's get started. Okay, first of all, when I say active matter, hang on, I need to, when I say active matter, I mean collections of particles that are powered. They could actually be alive, or they could be artificially powered. But the basic point is they're particles which are taking up free energy from a fuel tank on board or from their surroundings and turning it into work. And they keep doing this. So they kept going by a constant supply of free energy. So detailed balance is broken at the scale of the particle. And collections of particles, material made out of collections of such particles, is called active matter. Obviously, the definition was so that we can take living stuff and think of it as a kind of condensed matter. And that's why this category is defined. And obviously, interesting examples of it exist on scales from subcellular to oceanic, for that matter. And you can make interesting artificial versions of it, which I'll mention little by little during the talk. There are lots of review articles on the subject now, and these are just 2 reviews and a sort of short stock taking, which I thought you might find interesting. Okay, and active particles sorry, I seem to have, one of my favorite examples of active matter is this millipede flock, which is real live liquid crystalline order in a collection of objects moving as they go along. So both the particles of which active systems are made and the macroscopic state of those systems have various kinds of symmetries. You can have particles that have a vectorial character. They have a head and a tail and a structural distinction between the two ends. You can have particles that are elongated but are structurally the same at the two ends. Or you can have particles that are structurally apolar but have a direction of motion. And these kinds of particles can organize themselves into macroscopic phases with broken, say, rotational symmetry of various kinds. You can have ones that have a macroscopic polarity. You can have different versions that don't. You can have states with no macroscopic polarity, even made out of particles with a polarity, and so forth. You can also have collections of particles on which you can't discern a vectorial or a uniaxial character. You can just have little droplets that are carrying out a chemical reaction and running around like these self-propelled drops of Shashi Tuttupalli. These particles can be in a dynamical regime in which what one of the particles does strongly affects another particle, such as when you've got objects swimming in a fluid medium. So if you've got bacteria swimming in a fluid medium, what a given bacterium does sends momentum through the fluid to other bacteria. So this we call wet active matter. Or you can have stuff that's just lying on a solid substrate and moving around like these. This is a surface that's vibrated in the vertical direction. You have a top view here. Each particle is taking up some of that energy and moving back and forth. But clearly what one particle does and the momentum that one particle loses to the substrate is really not affecting the other particles. And we call this dry active matter. Active fluids are, that is wet active matter, is a particular interest of mine. And there's a short sort of opinion piece on the topic, which I wrote recently, which you may find interesting. Okay, and obviously you can get active matter, the same theme, if you like, of self-propulsion and particles disturbing the medium around them and affecting each other can take place from scales as small as the nucleus of the living cell to huge organized flocks. And it's really the same theme over and over again. And you can make interesting model systems. You can make systems where you take material of biological origin, such as molecular motors, filaments, and fuel, and reconstitute them in a purified system. Or you can make purely mechanical or purely chemical toys that imitate this motion. And actually, Leibniz is very aware of the fact that living stuff is a machine of which each little part is a machine. This sentence from Leibniz, quoted by Needleman and Dogic, really says that each component of the system breaks detail balance. That's really what it means. And of course, our aim is to understand living stuff as condensed matter. And if you like, the success of active matter has come in part from the fact that we've tried to keep things very simple and not be overambitious, focus on mechanics, on motility, on forces. And only now have people started taking timid steps in the direction of signaling, sensing, and so forth. And the more sophisticated biological effects are probably not a major part of active matter yet. Okay, so that's active matter. We want to talk about collections of powered particles. What about non-reciprocal interactions? Well, we're very familiar with the non-mutuality or non-reciprocality of interactions in social life. You know, one person can be attracted to another, the other person can be repelled by the first one. You can have effects of that sort taking place in systems that people have studied in the context of flocking, like apparently the alignment interaction of locusts. It turns out is because the locust at the back wants to eat the locust in the front, and the locust in the front wants to run away from the locust at the back. And similar kinds of asymmetric interactions have been explored in sort of a living context, in the context of neural net models, where you want to store temporal patterns and so forth. So I don't know why these stray slides are appearing here, sorry. This is the one I wanted. So what I wanted to say is that non-reciprocality is ubiquitous in the living world. And in today's talk, I'll tell you 4 stories about non-reciprocal or non-mutual interactions. These ideas have been explored in a lot of papers recently. Work from Surapray Saha, Ramin Golestanian, Ewan Marchetti and others, Fruscia and others in Vincenzo Vitelli's group. So these ideas are very much in the air currently, both in context of general models of condensation and phase separation out of equilibrium to models of systems made of spinning particles and so forth. Okay, so I'll tell you 4 very different stories, but with this common theme. So let's get started. My interest in non-mutual or non-reciprocal interactions actually goes back to long before we talked about something called active matter. Just as at least my own interest in self-propelled systems was beginning, with Jaijit Das and Madan Rao, we began to wonder about not a self-propelled system, but a kind of generic non-equilibrium equation of motion for the isotropic magnet. So you've got spins, each spin can point anywhere in 3 dimensions, and each spin precesses around the local field. That local field, apart from whatever you impose from the outside, is due to the spins at nearest neighbor sites. But you could imagine a situation in which the field felt at site I due to site I plus 1, and the field felt at site I plus 1 due to site I come from a different exchange coupling. Now, you can't imagine that in systems at equilibrium whose dynamics is governed by an energy function, because then only the symmetric part of the exchange can come in. But you could imagine that in a generic out of equilibrium system. And what we did was to say that if you had a system with a preferred direction and some kind of sustained non-equilibrium energy input, then if there was no symmetry, as I said, the preferred direction, if x and minus x are not equivalent, then you can have a situation where the spin ahead of a given spin affects this spin differently from the way this spin affects the spin ahead of it. And this turns out to give rise to a bizarre range of phenomena, including all kinds of instabilities in spatiotemporal chaos, which was the substance of this very early foray into non-reciprocal interactions. The idea basically is, imagine you've got 2 spins pointing in different directions. You can have, if you have an interaction of this sort, you can imagine that this spin does less of the turning to point the same way as this one, and this one does more of the turning to point the same way as that one. And this idea is what drove this work. And this idea came back to our minds in a very different context, namely flocking models. Okay. So with my student Lokarshi, another student Jitendra, Rahul Chhajwa, and my former student Ananyo, we started looking at XY spin models. And the sort of the short message of that work, which I'll now describe, is that you can get long-range order in XY spin models without the spins moving. Okay, so let's imagine you've got a bunch of little unit vectors, which I'll call pi, situated at space points labeled by I. And imagine that they are little rotors, mechanical rotors, and the rate at which they turn is governed by their spin angular momentum about their own center of mass. So then the rate of change of pi will be SI cross pi divided by some inertia. And the rate of change of SI will be pi cross, will be given by an aligning torque in which the rotor at site I tries to align with the rotor, turns to point parallel to the rotor at site J via a coupling Jij. And imagine if Jij and Jji are different if the 2 spins are situated at sites one in front of another as defined by P. Okay, so it's really this same idea that this guy is in front of this guy, so this guy affects this guy differently from how this guy affects that guy. And let's say you introduce damping because the system is sort of to be thought of as being on a medium with dissipation. This antisymmetric piece of Jij has very interesting consequences. Notice I started talking here about flocks, but I've specialized instead to a model in which the spins aren't running anywhere. You don't need to think of these P's, these spins, as the vectors of particles in a flock. You can think of them as just little mechanical rotors which only point but don't move. So here's your equations of motion. And supposing you have, as I said, Jij now is some J plus a constant times the projection of the separation between the spins onto the direction in which the spin is pointing. Okay. So then what will happen is this guy will feel a coupling J minus A due to this guy, and this guy will feel a coupling J plus A due to that guy. If these really were creatures that were moving, you can imagine that the guy at the back sees the guy in the front better than the guy in the front can see the guy in the back, and therefore the response is different. Nevertheless, even though these guys aren't actually moving around, if you take a model like this and coarse grain it up, go to a continuum description, then this bit will go to P dot is S cross P, and this bit will go to S dot has a piece which is P cross the first derivative of P in the direction of P. Now this looks complicated, but all this is saying is that you get a conventional aligning interaction P cross del squared P as you would in a Heisenberg magnet, but you also get this P cross the first forward space derivative of P. This sort of model with orientation and turning inertia without asymmetry has been explored in inertial models of flocks by Irene Giardina, Andrea Cavagna and group, Yang and Marchetti and others. But in fact, this model harks back to something very nice and pedagogical. It's discussed in Chaikin and Lubensky's book. It's just a rotor lattice. So P dot is S cross P, S dot is P cross del squared P. If you just introduce this weird fore-aft asymmetry, very interesting things happen. Now, first, if you remove the asymmetry, you have the rotor lattice physics, and you get, so you've got these rotors, and disturbances in their orientation propagate as waves with a speed given by the square root of this stiffness divided by inertia. If instead you go to the long time slow behavior, saying that on times long compared to the relaxation time, you can forget the rate of change of this spin angular momentum, then S is determined by P through this equation where you throw away del S over del P, del T. So you can then take this S and replace it by this expression. And what you get is an equation for P, which has a del squared P and a P dot grad P. This 1 minus PP is because P is a unit vector, not so important. The point is, P ends up advecting itself even though P isn't a velocity, even though these little rotors aren't moving. The simple fact there's a fore-aft asymmetry in their interaction, and an asymmetry that doesn't come from an energy function, makes P carry information about the local orientation here in the direction in which it is pointing. So this equation is actually has the essentials of the Toner 2 model of flocks. You've got an orientation. That orientation acts like a velocity. It acts exactly as though the P's are all moving along with a speed given by the value of their orientation vector. And if you augment this with noise, you get equations of motion for an orientation field, which, thanks to this funny advection term, actually has long-range order in 2 dimensions. So the essential physics that allows the Toner 2 model to have long-range order isn't that the spins are moving, it is that the spins have a fore-aft asymmetric interaction in which the effective exchange coupling of something ahead with something behind is asymmetrical. So all it takes is non-mutual interaction, not motility, to get a long-range ordered spin system in 2 dimensions. There's other interesting byproducts of this. It turns out if this fore-aft asymmetry is too large, you actually get an instability and the whole structure dissolves into chaos. But that's not the most important point. I think the most important point here is simply that non-mutuality makes the orientation advect itself just like it is a velocity. Okay, and one can study these features further and the instability, but I want to go on to my next topic as I'm running a little behind. Perhaps if you have any questions, essential questions on this bit, I'll pause briefly now. Richard, is that okay?
That's fine. As yet, there's nothing in the
questions?
Q&A, and there's nothing in the chat. So,
okay, so
I would say
I'll go ahead. Right?
Fire on.
Okay. So summary of this part is that 2D XY long-range order doesn't need motility, it only needs non-mutuality. And the non-mutuality makes the polar order parameter carry itself, transmit gradients in its own, inhomogeneities in its own orientation as though it were moving. Okay. All right. Let me go to a rather different example of non-mutuality. I spelled that right? Yes. Okay, so that's flying or non-mutual XY models. A very natural setting in which non-mutuality arises is in active colloids. So if you take a particle which is partly coated with a catalyst and put it in a medium which contains a compound that this catalyst breaks down, then on the surface of this particle, you will get an inhomogeneity in the concentration of the reactant, and you will get a kind of slip flow along the surface, which will turn this particle into a motile particle. So these particles, this is shown by the group at Penn State, Sen and others. A theory of it was given by Golestani, Najdari, and Liverpool. And what you'll see is the particles run around. On long times, they move randomly just because there's noise and there's very few particles. But it's certainly not a conventional random walk. It's very, very persistent motion because of self-propulsion. So these self-propelling objects, if placed in a gradient of concentration, let us say of this reactant field itself, can then turn. So now what you have is particles. You've got a particle, it's surrounded by, you've got an active colloid, it's surrounded by a concentration field of reactant. It moves in a direction set by the way in which its catalytic cap is pointing. But in general, if you have an inhomogeneous reactant field, then if the catalyst cap is pointing in an arbitrary direction, it will tend to get reoriented by the reactant field. Okay, so the reactant field, a uniform reactant field propels, an inhomogeneous reactant field reorients. So now if you have two particles immersed in a reactant field which is uniform far away from the particles, you'll have gradients in the vicinity of the particles. So if you have these two particles, this one will sense that one's presence thanks to the reactant gradient. It will reorient. This one will sense that one's presence, reorient. They can move towards each other, away from each other. In general, the point is the propulsion is set by the way the particle points, but the direction of propulsion can be changed by reorienting the particle. The result is that you can have a situation in which you have one particle turning to point to another particle, the other particle turning away, and they can pursue each other. So you can get fantastic kinds of pair dynamics in this system. We've explored it really mainly in a problem of two particles in this case, and outlined the situations in which you get strong non-reciprocality and very interesting orbits like these waltzes and things. But we haven't, at least speaking for myself, I haven't really explored the larger implications of this. This is work done with Sriram Saha and Ramin Golestanian. And the summary of this second part of the talk is really that non-reciprocal interactions are natural and inevitable in self-propelled colloids. You get amazing orbits. Whether you can harness the possibility of steering the particles, whether you can create spatially organized structures, etc., is something which we'd like to do, but we haven't done. There's an article that came out last year which summarizes this work. Okay. A third, again, if there's any question, No, right?
So Sriram, I think actually Michael might have a question. Michael, do you want to ask that?
I can do that. So if you only observe one of your pair of dancing particles, can you tell that it has a partner, or could it be just an independent particle in some weird liquid?
Well, it could certainly be an independent particle in an imposed concentration background. It's like, so first of all, it's a little bit like the two-body problem in mechanics.
Yep.
You can, but it's different. There isn't really a conserved momentum. The thing that acts like inertia is the persistent motion of the particle.
Yep.
So whether I can, my guess is I'll be able to tell that it's one of a pair. I think so, but it's a good question. I haven't, if let's say the other particle is undetectable or small, whether I can tell that the other particle is there. I think I can, but now that's the best answer I can give you. I think I can, sorry.
So then the other question would be the follow, and would there be an asymmetry between the follow or the leader particle? Which one could you tell more easily is under the guidance of some other dance partner?
First, imagine these are two particles of the same type.
Yes.
Then within this model, you can still certainly get non-reciprocality in the sense of chasing and running away. And that's because the disturbance field that one particle sets up in the surrounding medium, as it moves, actually has an asymmetry. So what can happen is if you've got one particle here, it's got a solute cloud around it, and it's moving along. So in principle, that solute cloud has a structure that's different in front and in the back. Therefore, what can happen is this particle can sense that particle's solute cloud better than in a different way from how that particle senses this one. So you can the leader and the follower will certainly be different if that's what you were asking.
Yeah.
And in fact, the next topic I'm going to discuss, which is motile particles in an elastic medium, illustrates it rather dramatically. So maybe I can show you that. Should I go on?
Yeah, there's no more questions in the thing, so why don't we keep going?
Okay. Now, in the literature on self-propelled particles in an ambient medium in which the ambient medium has a dynamics, most attention has gone to the case where that medium is a fluid. Okay? But you can imagine self-propelled particles moving through an elastic medium. That elastic medium could be the extracellular matrix, or it could be an epithelium of not so motile cells in which you have a few motile cells moving around. These issues have been broached in work by Safran and Silke Henkes. But in Safran's work, they looked at force dipoles, non-moving force dipoles in an elastic medium. They ignored motility. In Silke Henkes' work, they looked at active Brownian particles in an elastic medium, but they didn't look at them reorienting each other through the medium. So we decided to look at the problem of active particles in an elastic medium. This is work that is still under review. It's by my student Rahul Gupta, Harsh Soni, Ajay Sood's student Roshan, and Ajay. So there's a story with experiments and theory and simulations here. All right. Now, in work a few years ago, we showed that if you have particles moving through a dense monolayer of beads, then the flows that one moving particle sets up orient other particles to point the same way. Okay? And the way it happens really is this. Here's one particle, it's moving along. As you can see, this is a simulation. We've colored a few of the particles to show you what's happening. As this particle moves, it drags particles, and that actually sets up a flow which, sorry, it's a little small, has this dipolar character because it's on a substrate. If you increase the concentration of the ambient medium, the beads in this case, so the medium becomes crystalline, then a moving particle, which initially started from here, doesn't really drag the medium with itself. So the question is, what does happen? So both in a fluid and in a crystalline bead monolayer, the motile particle is able to move. When the monolayer is fluid, there are flows around the motile particle. When the monolayer is crystalline, there's some little random disturbances, but no flow. So what does happen? Well, you can do theory on this. You can say that my motile particle has a dot is missing. That should be R dot is V0 N of T. Particle position R, orientation N, displacement field of medium U. So we're taking an elastic medium. And let's say the medium is governed by some standard Lamé elastic free energy. And its medium is on a substrate. That substrate has a friction damping constant zeta. And so we write down on very general grounds the following model, that the particle velocity has a fixed magnitude and takes place in the direction which the particle is pointing. It's this kind of particle. Okay. This is an experiment on a vibrated surface, and this elongated asymmetrical particle is transducing the energy of that vibration into motion in the plane, and it's able to plow its way through a bunch of beads around it. And the orientation of a given particle in the presence of a displacement field in the medium can respond either to the strain field of the medium or to gradients of the strain field. So here the idea is if you've got an extensional or if you've got a stress in the medium that is locally extensional in some direction, then you can imagine that a rod-like particle likes to line up with the extensional axis. You can also imagine that if there is a bend or a splay of the crystal planes, or the crystal lines in this case, those could also reorient the particle. This effect is clearly higher order in gradients than this one, so we'll focus on this one. Experimentally, it turns out this part is really small. Okay, so then how does the particle affect the medium? The medium left to itself, because it's on a substrate, has a damping. We ignore inertia, so you would think it will relax to equilibrium with respect to a standard elastic free energy F. But if you put the particle into the medium, that particle is pushing its way through the medium, and it becomes a little point force. This is a force monopole. It's perfectly okay to have a force monopole here because you've got a substrate to take up the slack of momentum conservation. This force monopole forces the elastic medium, and so the elastic medium now is not relaxing to equilibrium. Its steady state is a balance between forcing and elasticity. So what happens? Well, what happens first is if you take one particle and co-move, imagine you have one particle otherwise in an unbounded elastic medium, co-move with it, then the du over dt in the co-moving frame becomes a directional derivative along the direction of motion of the particle. So the steady state elastic deformation in the medium in the particle's frame becomes that of a force monopole in the presence of a combination of elasticity and advection. So that means the displacement field is not the elastic Green's function of the medium, but is crucially modified by this bit. And so you get displacement fields around the particle given by Bessel functions by modified Bessel functions K0 and K1. The really important feature is, if you look at the asymptotic properties of these Bessel functions, is that the strains are highly screened in front of the particle, exponentially screened, and right behind the particle, they are not screened at all. They decay as 1 over the square root. Oh, I didn't. Okay. So if you just, alpha, I'm sorry, I didn't define. Alpha is a length scale that comes out. Alpha is a length proportional to 1 over the self-propelling velocity, and of course involves elastic constants. So a moving particle, therefore, has a disturbance field which is highly damped in front of it, highly screened in front of it, and power law decaying behind it. So it's like it has an overdamped elastic wake behind it. Each particle moves along, leaves a wake. It's kind of like a stealth particle in front of it, but you can detect it if you're behind it. And you can actually measure these fields in a sort of detailed, a slavish recreation of the experiment in a simulation. It's fairly complicated to do the measurements because you have to match the density wave patterns with and without the particle, but it can be done. And you find this characteristic rapid fall off in front and slow fall off behind in the theory, which is nicely reproduced in the measurements. And so you can then ask, okay, that is one particle. what happens if you put another particle into that medium? You put another particle into the medium, two different things happen. Alignment with the strain turns out to be crucial, and what it does is, if you say the rod aligns with the extension axis, then if you have two particles, each of them, the strain field produced by the one particle acts on the other in such a way as to reorient them to point towards each other. So two particles initially released parallel to each other turn and find each other. And that's the important point. This bit is really subdominant. I won't talk about it. Alignment with the principal axis of the strain is crucial. And so you can measure these in experiments on a vibrating surface, like I was saying. And the particles, as I said, acquire motility because when they're tossed up and come down, they're impelled forward because they typically land fat end down rather than skinny end down. And so you can measure what happens with two particles. You find that if the medium is fluid, two particles move away from each other because that's the way the flow fields they set up turn them. But if the medium is elastic, they do indeed catch up with each other. In these experiments, the two particles are released side by side. This is the experiment. The simulation really does the same thing. And there is some distance dependence because if they're too far away, the noise intervenes and makes them lose their way. What's really fun is if you take two particles, one of which is moving along this way and the other is released pointing this way. So then what happens is the one particle is approaching the other particle from behind, and the theory at the level of this pair dynamics says that the particle in front is very dimly aware of the particle behind because that particle's strain field is highly screened. The particle at the back can see the particle in front because its strains are highly undamped, and so it is turned to point to this one. And in fact, the first phenomenon we saw in the system was in the experiments and the simulations, the particles always tending to do this chase from behind and get trapped. So this sort of robust prediction of the theory is nicely borne out in experiments. So elastic interactions of active polar particles are non-reciprocal. Capture is strikingly non-reciprocal. I don't know if the living world has made use of this trick, but it's hard to see why it wouldn't. So I do hope someone will go look for it in some experiment with a biological context. I'll now move to a somewhat quick presentation of the last part of my talk. A very different manifestation.
Sriram, can I interrupt you just very briefly? Sure. So there was a question, and in fact, I also need to apologize to John Sunil, who asked it because I actually saw it a bit too late. But he asked, how is the Lamé free energy defined?
How is it defined? Meaning, how is it expressed? How is it? It has a standard form. There's a bulk modulus and a shear modulus. From our measurements, we can infer dimensionless combinations of the elasticity, and meaning that the equations have a lot of parameters. You can non-dimensionalize them, and you can measure the strain fields produced by a moving particle and back out these coefficients. Now, the reason the system has a Lamé elasticity is that it's visibly crystalline. It has no energy scale other than what you're giving it by shaking, and therefore there'll be something resembling an effective temperature. And just as hard sphere elastic constants are defined by temperatures and particle size scales and volume fractions, the same thing will happen here. But I have no idea of a microscopic calculation that will take me from a vibrating layer of beads to a Lamé elasticity.
Sorry.
Yeah? Sorry? I can't hear. Can you hear me? Oh boy.
Hi, sir. I'm sorry. I was wondering, is it possible that in this crystal phase you would expect some kind of hexatic ordering?
Yeah. So actually, this is the bead monolayer phase diagram is fairly well studied, I think, by Urbach and company. You do seem to see crystal, hexatic, and liquid. We haven't worked out the dynamics of rods in a hexatic medium from first principles theory.
And Sriram, I'm also going to take a big liberty here and ask you a question, but I promise I'll let you go after that.
That's
which
fine.
is that, can this be viewed as a sort of active plasticity, in the sense that these moving particles are inducing a bit like defects that are sort of being driven around?
Is, you have plasticity and non-affine motion close to the particle, but if you look at the far field structure of the medium, it's just an elastically strained medium.
Right.
So, I mean, it's a bit like an ice skater melts the ice under the skates, but the rest of the lake is still ice, roughly.
Okay. Cool.
Yeah.
Thanks.
And I mean,
I'll let you go.
I think the mechanism for how these things move is very interesting, but you can get away without understanding the mechanism if you look at the far field and if you just say it is moving. But I think there is interesting physics in how it moves also, which we have not explored sufficiently.
Okay, thanks.
Yeah. Okay, and now to active cholesterics. Symmetric liquid crystals and cholesteric liquid crystals are two completely different examples of a system which has a one-dimensional periodic structure. In the symmetric, the periodicity is in the density. You have layers, dense regions where there are particles, and slight regions of lower density where there aren't particles. So here you have well-defined layers, the layers being the density maxima. These are achiral. A cholesteric has an orientation wave. The director twists continuously from one Z position to another in this manner. Any horizontal slice is the same as any other horizontal slice, in the sense that there's no occupancy, there's no density modulation at all, so there's no true layers. It's completely arbitrary which you call the layer. You say that I will call things that are pointing east-west the layers. In that case, this is a layer, that's a layer, and so forth. You can think of it that way. But there isn't. But despite this detailed structural difference, the macroscopic fact that both have a one-dimensional periodic modulation endows them, it turns out, for systems at equilibrium with identical long wavelength dynamics. Okay, the hydrodynamics of an equilibrium cholesteric is identical to the hydrodynamics of an equilibrium symmetric, because both of them are basically one-dimensional springs with a fluid layer structure in the direction transverse to the springs. So the chirality is completely cloaked from any of the long wavelength hydrodynamic properties, damping, you name it. All the interesting properties of cholesterics, the interesting hydrodynamic properties of cholesterics are actually, in a formal sense, subdominant to their true long wavelength theory. What about active cholesterics? So this is work done with my student Swapnil Kole in collaboration with Ananya Maitro and Gareth Alexander, build active cholesteric hydrodynamics. So we're going to take a very easy route to this. I seem to have hit the 45-minute mark, but we started a little late. So let's say a cholesteric is a one-dimensional wave of any scalar plus chirality. If you like, it's a one-dimensional wave of any pseudoscalar. Okay? And yeah, so I don't really care what psi is. It could actually be a symmetric, it could actually be a density wave together with a bunch of homochiral particles sprinkled in the system, or it could be a true cholesteric defined by a director field. I don't care. I believe the long wavelength dynamics of the two are the same. And that psi acquires a one-dimensional modulation along Z. Distortions of that one-dimensional modulation are described by a displacement field. You can write down on general symmetry grounds the simplest, that is, the fewest, the chiral stresses not obtainable from a free energy and with the fewest number of gradients. So for a three-dimensional system, it turns out this is the minimal object that you can write down. Z sub chi is just a coefficient. Epsilon ijk is the antisymmetric tensor, and you have this. Okay. You can also ask about a two-dimensional cholesteric, two-dimensional chiral layered system. So you have a bunch of stripes, and it's made. Imagine taking a three-dimensional chiral material, taking a thin sheet of it, making a striped phase in it, and endowing that sheet with a preferred normal in one of the two directions. So let's say you've got a sheet on a substrate or a sheet with a vectorial asymmetry in a direction perpendicular to the sheet. You can then define from this three-dimensional epsilon tensor, you can define a two-dimensional epsilon tensor and you can have an active stress in 2 dimensions that look like this. So when I call these active stresses, I mean these are stresses allowed by the spatial symmetry of the system, but not derivable from a free energy functional. So these are the 2 systems we study. And if you take this one and plug in a density wave form into this psi, you find that you get a force density. This is a 3-dimensional case. You get a force density for which the local mean curvature of the layer acts like a stream function. So the force density is the 2-dimensional curl of the local mean curvature. That means this is an active chiral force density pointing tangent to contours of constant mean curvature. So if you've got a layer and you've got a bump on it, you have a force density pointing with a given handedness around that bump. I'll show you pictures where you'll actually see this. Okay. This object is a little bit different. 2 and 3 dimensions are different because a 2D chiral system, as I said, is a slice of 3D chiral material together with a preferred you've got a sheet like, you've got a layer like this, and you've got a defined preferred upward normal. Okay. Now let's talk about the 3-dimensional system to begin with. 3-dimensional layered systems, in addition to the chiral active stress, also have an ordinary active stress. That is, you can build a term bilinear in gradients of psi, which, if you express it again in terms of the density wave, turns out to amount to an internally generated tension or compression in the layering direction. Now, if you have a layered system and you pull on it, you apply a tension on it, then in an effort to keep the layer spacing constant, it's well known, this is the Helfrich-Huro instability, the layers undulate. Because pulling on the layers turns out to give the system what looks like a negative tilt modulus. So the layers want to tilt. On the other hand, the layers want to not bend too much. So you get this interesting structure. This is called the undulation instability, is a well-studied property of symmetric electric crystals under externally imposed tensions. The uniaxial achiral active stress makes these systems have such an instability. This is something we discussed a few years ago in work with Tapan Adhyapak and Gareth, John Toner, and others. So if it wasn't chiral, you just make the system undergo a spontaneous undulation instability. But if it undergoes an undulation, then this term kicks in. And what happens? What's my time like? What happens basically is that the undulations create a state in which you get spontaneous flow circulating vertically, alternating in sign. You have, let us say, anti-clockwise here, clockwise here, clockwise here, so anti-clockwise surrounded by clockwise. So a whole array of these things. So basically, you have a layered system with chirality. You switch on activity. If the activity is such as to create the undulation instability, you immediately get a vortex lattice. The other cool thing is this. You can reach in by hand and suppress the undulation instability by applying a compression. So in practice, it's easier done by applying electric fields for technical reasons. But the point is basically what you have is a system where you can squeeze on it, and it's a perfectly nice layered system. You decrease the squeezing, and it undergoes an undulation instability. The moment it has an undulation instability, it will acquire this vertical pattern of flow. So it's a sort of on-off switch for a self-stirring state. The reason that this is related to non-reciprocality is that if you write down the stresses, whether in 3 dimensions or in 2 dimensions, you will find, as I said, that if you look, for example, at this force density, you're creating a displacement field in the vertical direction and producing forces in the horizontal direction, in a direction in which there isn't even a displacement field. It's closely related to this thing called odd elasticity that Vincenzo Vitelli and group have talked a lot about. That you know that in any momentum conserving system, you can write the force density as a divergence of a stress. In a system with a strain field, the stress and strain are related by an elastic tensor. If the elasticity comes from an energy function, then this tensor is symmetric under interchange of ij and kl. So if it isn't, this is called odd elasticity. What we have here is a weird generalization of that kind of odd elasticity, in which you get relations, you get stresses due to layer tilt, which isn't even a strain because there's no shear modulus in a layered system at all. So it's sort of odder than odd elasticity, if you like. Okay, in 2 dimensions, you get a slightly different pattern due to the other term, which turns out to give you spontaneous shear flows in the plane, possibly leading to spiral states. You can kind of understand it in the following way. If you've got an array of things all made of wheels turning in the same direction, then if you push them together, they'll start shearing past each other. And that's what we've tried to. This is the calculated flow field just past the instability. Anyway, so the summary of this last part of my talk is that active cholesterics and active symmetrics aren't the same thing, even at the longest length scales. There are a new family of chiral stresses, and you can actually control the instability and a self-stirring state that you get in these systems by externally imposed stresses. There's interesting hints of transitions to spiral turbulence or something like it in the 2-dimensional case. Okay, and so that's the end of my talk. 4 stories, 2D XY long-range order doesn't need motility. Active colloids waltz and dance around each other as a result of non-reciprocality. We presented theoretical predictions of non-reciprocal interactions between polar particles moving through an elastic medium and showed you experimental and numerical evidence of those kinds of capture events. And lastly, active cholesterics aren't the same as active symmetrics. And there's this, what I think is a very pretty self-stirring instability, which you can control by external stress. Thanks very much.